Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. From last 3 lectures we are discussing about Green's theorem. In lecture number 20 we have discussed one example on Green's theorem, and in this lecture also we will discuss one question on Green's theorem which was asked in GTU Winter 2019 exam. They generally ask this type of question for 7 marks. The question is, verify tangential form of Green's theorem for this vector field f bar equal to x minus sin yi plus cos yj, and C is the boundary of the region bounded by the lines y equal to 0, x equal to pi by 2 and y equal to x. First we recall what is tangential form of Green's theorem. Suppose f bar is equal to m into I plus n into j, then line integral m dx plus n dy along given curve C is equal to double integral over region R of del n by del x, that is derivative of second component with respect to x minus derivative of first component with respect to y, and we have to integrate over this region R. R will be the region enclosed by given curve C. So here we are asked to verify this statement. So whenever they ask you to verify Green's theorem, you have to compute both the integrals. You have to compute line integral as well as double integral, and you have to show that both are equal. So whenever we have verification of Green's theorem, then remember that we must compute line integral as well as double integral, and answer of both must be same. Then only we can say that we have verified Green's theorem. So first we write down what are the components of given function. If we compare this f bar with mi plus nj, we find that m equal to x minus sin y and n equal to cos y. So first we write down given components. Here capital M is x minus sin y and capital N is cos y, and we have to find out value of line integral m dx plus n dy along curve C, and curve C is the boundary of the region bounded by these 3 lines. So first we sketch this region bounded by these 3 lines, then we will have idea about the given curve C. So given region is simple, it is 2-dimensional region in the xy plane. First we sketch this x axis and y axis, and we are given 3 lines. Y equal to 0, that is x axis. X equal to pi by 2 is the line parallel to y axis. So first we sketch that line, x equal to pi by 2. So suppose this line is x equal to pi by 2. Another line is y equal to 0, that is x axis, and third line is y equal to x. We know that y equal to x is the line which is having 45-degree angle with positive x axis. So suppose this is the line y equal to x, and first we write down all these things. This is x axis, y axis. X axis means y equal to 0. This is the line y equal to x, and this is the line x equal to pi by 2, and we have to find out the region bounded by all these 3 lines. So we can see this is the boundary of x equal to pi by 2, this is the boundary of y equal to 0, and this is the boundary of y equal to x. Therefore this is the region of integration, and the boundary of this region is given curve. So R is the region of integration, and we consider this as curve C. So curve C is union of three smooth curves. If we denote this part, this is from this point is 0 0, this line is x equal to pi by 2, therefore this point has coordinates pi by 2 comma 0. Here x is pi by 2 and y and x are equal, therefore this point is also pi by 2. So we have this point as pi by 2 comma pi by 2, and our curve C can be written as union of these three curves, C1 union C2 union C3. So we consider this line segment as C1, this line segment as C2, and this line segment as C3. So line integral along curve C will be equal to sum of line integrals along C1 plus along C2 and along C3. So first we find out value of line integral. Before that we write down our function m dy minus n dx. Line integral along curve C is m dy. Here we are using tangential form, so we will consider m dx plus n dy. If we are considering normal form, we will remember m dy minus n dx, but because we are considering tangential form, we are taking m dx plus n dy. Now we substitute values of m and n. M is x minus sin y and n is cos y. M is x minus sin y and n is cos y. This is equal to, now our curve C is the union of three curves C1, C2, C3. This is integral along C is sum of integrals along C1, C2 and C3. Now here C1 is not closed curve. Similarly, integral along C2 x minus sin y dx plus cos y dy plus integral along C3 x minus sin y dx plus cos y dy. Now we will directly use parametric representations for C1, C2 and C3. Now C1 is the curve along x-axis. So equation of C1 is y equal to 0, and we can see x lies between 0 and pi by 2. So along C1 y is 0, x lies between 0 and pi by 2, and because y is 0, dy is also 0. So along C1 we will consider y equal to 0, that is dy equal to 0, and x is from 0 to pi by 2. So that we substitute directly here. We consider x from 0 to pi by 2 along C1, y is 0, therefore sin 0 is 0. Here dy is 0 along C1, so we are left with x dx only. Because y is 0, therefore sin 0 is 0, and here dy is 0. Plus, now we check what we have along C2. C2 means line x equal to pi by 2, that is x is constant, therefore dx is 0 and y varies from 0 to pi by 2. So along C2 we use x equal to pi by 2 and dx equal to 0. So dx is 0, y is from 0 to pi by 2, x is pi by 2, but dx is 0, therefore this term will be 0. 0 into this quantity is 0, and cos y dy. Again I repeat, along C2 x is pi by 2, therefore dx is 0 and y is running from 0 to pi by 2. So because dx is 0, we are left with cos y dy only. And now what we get along C3, so C3 means along C3 y and x are equal, therefore we will put dy equal to dx, and x is running from pi by 2. At this point x is pi by 2, at this point x is 0. So limits of x will be from pi by 2 to 0, and we will put y equal to x. So here I have x minus sin x dx plus cos x dx, and then we will take this dx common and we will integrate with respect to x from pi by 2 to 0. Now we find out what is this integral. Integral of x is x square by 2. Limits of x are from 0 to pi by 2. Integral of cos y is sin y. Limits are from 0 to pi by 2, and here we can take dx common directly, and we have x minus sin x plus cos x. So let me write plus cos x here, and we are taking dx common. So if you wish, you can write directly also x minus sin x plus cos x, integral with respect to x. Integral of x is x square by 2. Integral of sin x is minus cos x, therefore we have plus cos x. Integral of sin x, integral of cos x is sin x. Limits of x here are from pi by 2 to 0. Now we substitute values of upper limit and lower limit. For this, upper limit is pi by 2, lower limit is 0. And here we have square of x, therefore we will have pi square by 4 divided by 2, that is pi square by 8. Here upper limit is pi by 2 and sin pi by 2 is 1 minus sin 0 is 0, plus here upper limit is 0, so this is going to be 0, sin 0 is 0, and we have cos 0 equal to 1. So first I write 1 for upper limit, minus for lower limit x is pi by 2. So if I take x equal to pi by 2 here, I will have pi square by 4 divided by 2, that is pi square by 8. Cos pi by 2 is 0 and sin pi by 2 is 1. And we simplify this. This I can rewrite as pi square by 8 plus 1 minus pi square by 8 minus 1. So pi square by 8 will cancel out, this 1 will cancel out, and value of line integral along given curve is 1. Therefore integral m dy minus m dx plus n dy, we have tangential form, so m dx plus n dy equal to 1, and we give this number 1. Now we find out double integral over this region R, and our answer must be same whatever answer we have obtained for line integral. For line integral our answer is 1, therefore value of double integral over this region must be 1. Now for double integral, first we have to decide whether we want to integrate with respect to x first or with respect to y first, because we have to decide the limits of integration. So suppose I want to integrate with respect to y first, then I will consider a vertical line passing through the region of integration. To decide the limits of integration for double integral, I consider a vertical line passing through the region, and I concentrate at the points at which line enters the region and line leaves the region. Line enters the region on x-axis. So here we can write that line enters, and it enters at x-axis. So we can say that equation will be 0, or value of y will be 0 at this point. Line leaves the region on the line y equal to x. So we can write that line leaves at y equal to x. So if we consider this part of the line, then along this part x becomes constant and y is varying from y equal to 0 to y equal to x. Therefore, limits of integration for y will be from y equal to 0 to y equal to x. And for limits of x, we will consider the leftmost point of the region and rightmost points of the region. All these points are rightmost points, and there is only one leftmost point. At this point, value of x is 0, so lower limit for x is 0. At this point, value of x is pi by 2, so limits of x will be from 0 to pi by 2, and we have to obtain this quantity also, del n by del x minus del m by del y. N equal to cos y, so there is no x here, so cos y is constant, therefore its derivative is 0. Del m by del y means we have to consider x constant, so derivative of x is 0 minus cos y. Derivative of sin y is cos y, and this minus minus plus, therefore this quantity del n by del x minus del m by del y becomes cos y. So we have to integrate this function cos y over this region, for which limits of integration we have obtained as y from 0 to x and x is from 0 to pi by 2. So first we write down what is this del n by del x minus del m by del y. So as I discussed, n is independent of x, therefore its derivative is 0. M equal to x minus sin y, derivative of x is 0, derivative of sin y is cos y, so this is cos y. And we can see, or we can shortly write that the region R is shown in figure, and we can write that the limits of integration, are y is from 0 to x and x is from 0 to pi by 2. And now we evaluate the double integral over given region R. Double integral of del n by del x minus del m by del y, and we have taken order of integration as first with respect to y, then with respect to x. This quantity we have obtained as cos y, so we integrate cos y with respect to y from y equal to 0 to x, and while doing this integral we will consider x as constant, and after that we integrate with respect to x from x equal to 0 to x equal to pi by 2. So integral of cos y is sin y, and the limits of y are from 0 to x, then integral with respect to x with limits 0 to pi by 2. First we put upper limit is y equal to x, and this is from 0 to pi by 2. Upper limit is y equal to x, that is sin x, minus y equal to 0 will be 0, sin 0. Sin x minus sin 0 is 0, and integral of sin x is minus cos x, and limits of x are from 0 to pi by 2, and this is equal to minus cos pi by 2 upper limit minus minus plus cos 0. Cos pi by 2 is 0 and cos 0 is 1. Therefore we can see that value of double integral is also 1, which is same as value of line integral. So Green's theorem is verified. We evaluated line integral first. This is number 2. In equation 1 we have obtained the value of line integral, and it turns out to be 1, and value of double integral is also 1. Therefore we can say that Green's theorem is verified. From 1 and 2 we obtain that m dx plus n dy, this is equal to double integral of del n by del x minus del m by del y over region R. So we can write that this verifies tangential form of Green's theorem. So they can ask you to verify Green's theorem either in tangential form or normal form. So whatever form they ask you to verify, you should find out line integral as well as double integral. If they don't specify that which form you have to verify, then you should go for tangential form. So whenever it is specified, you should use specified form of Green's theorem. If nothing is specified, we will go for verifying tangential form of Green's theorem. So here in this question we have first computed line integral along this curve, and you can see it is easy to compute double integral as compared to line integral, because here we have to consider union of three different curves, and line integral along this curve C is the sum of these three different line integrals. So for each curve we have different parametric representation, so more work is required for line integral as compared to double integral. In double integral we are able to compute easily, so that is the power of Green's theorem. But if they ask you to verify Green's theorem, you should compute line integral as well as double integral and give this as number 2, give line integral answer as number 1, and then you should write that from 1 and 2 these two are equal, therefore Green's theorem is verified. So this is all about this session. I hope you like it. Thanks for